Welcome back yet again to another exciting episode of Dave Does Math from Home. Today we're going to talk about section 13.3, dot products. So we have worked with vectors so far by multiplying them by numbers. We call that scalar multiplication. So we can do scalar multiplication and we can do sums and differences of vectors. That's all very straightforward. It works exactly how you would expect it to do. The problems are going to start creeping in, as in most of calculus. Addition and subtraction coefficients work really well. The problems start to come in when we start trying to multiply things together. That's sort of like the constant theme throughout all of our calculus courses. Multiplication, or addition, subtraction, coefficients are safe, multiplication is not. So, today we're going to learn one of the ways to multiply vectors. I say one of the ways because there are widely accepted to be two different ways to multiply vectors. They work completely differently and they give you completely different answers. They have no relation to each other except that they both involve multiplication in some way or another. If we were doing this live in person, I would have an enormous amount of fun asking for ideas how to multiply two vectors together and seeing what you guys came up with and testing those ideas and seeing what that might mean or what might imply. This isn't live and I can't ask you questions, so I'm just going to tell you how to multiply two vectors. Let's say we have u is, let's start nice and simple. Let's go 1, 2, 3. This is a vector in 3 space, 1 left, or 1 right, 2 up, 3 out. And let's say that b is -4, 0, and 2. This is 4 right, 0 up, 2 out. The way that you multiply these using a dot product is you multiply the corresponding parts and then add those together. So, u dot v, oh, I should say, these are called dot products. I mentioned that there's another way to multiply vectors. Those are called cross products. And the reason that this is a dot product and the other one is a cross product is the symbol changes. Throughout all of the rest of math, we have used these two symbols interchangeably because they both mean multiplication. When you're only working with scalar numbers, they both mean multiplication and they mean the same thing. When you're working with vectors, these mean two completely different kinds of multiplication. So, that's the dot product, that's the cross product. One of them uses a dot, the other one uses a cross. Pretty self-explanatory. We're going to talk about cross products in section 13.4, so be patient for that one. They're a lot weirder than dot products. Dot products are sort of the natural first step. So we'll focus on these for now. And we're going to get this by multiplying the corresponding pieces together. 1 times -4 is -4, 2 times 0 is 0, 3 times 2 is 6, and then sort of the tempting thing to do is to create a new vector out of this, but that's not how dot products work, and that new vector doesn't mean anything. Like there's no geometric meaning to creating a new vector out of the products of corresponding pieces of two other vectors. It's not useful in any way. If we add these things together, instead of creating a new vector out of it, we'll get that the dot product here is 2. It's a little weird that when you multiply two vectors together, you don't get a vector. The dot product of two vectors is a scalar number. There's no i's or j's or k's here. Doesn't have any brackets. There's no other piece to this. It's literally just the number 2. The product of these two vectors is the number 2. So we're going to talk a little bit about what this means and what it's for. And to do that, I'm going to slip back into two-dimensional space so that I can actually draw these things. Let's talk u equals 4i plus 5j, and v equals 5i plus 4j. These two vectors are right here, and u dot v in this case would be 20 plus 20 is 40. Let's do u as 3i minus 7j and v as 6i plus 2j. These vectors are here, here's u, and here, here's v, and the dot product here is positive 18, negative 14, this will be a negative 4. Let's do u is 5i plus j, and v is negative 6i minus 2j. Here I'm going to have 5i plus j is right there, negative 6i minus 2j is down here, and the dot product is negative 30 minus 2 is negative 32. At this point, I would like to encourage you all to pause the video, come up with another 5 or 6 examples of two-dimensional vectors that you can easily draw, easily find the dot product of, and just sort of fill a sheet of paper with things that look like this. Two vectors, their diagram, their dot product. Two vectors, their diagram, their dot product. So pause the video, do that for 5 minutes, make some nice vectors, and then come back to this. I will assume that you have all done that. Hopefully, the pattern that we're sort of starting to establish, if you've done this another 5 or 6 or 10 times, is that these vectors are kind of going in the same-ish direction, and their dot product is pretty big. These vectors are more or less perpendicular-ish. They're going in sort of right angle directions, and their dot product is very, very small. And these are going in almost exact opposite directions, and their dot product is very big and also negative. Based on this, you could pretty confidently guess that dot products are some way to measure the same directionness of two vectors. So, let's use this assumption and try another example and see what we get. I'm going to do something based vaguely on this. I'm going to do u is 40i plus 50j, and v is 50i plus 40j. These vectors are here and here. Both of these vectors are exactly the same as these vectors, but 10 times bigger. They are scalar multiples. This u is a scalar multiple of this u, this v is a scalar multiple of this v. So they point in the exact same directions as these original two, which means they should have the exact same directionness as the original. So let's see what kind of dot product we get here. U dot v in this case is going to be 2000 plus 2000 should give me 4000. Which is kind of a bit of a wrench in our plan. Based on these examples we did, and the hopeful 6 or 10 or other examples that you did on your own, we should have sort of reached this conclusion that dot products measure same directionness. But here we have an example of vectors that ought to have an identical set of same directionness. But one of them is 100 times bigger than the other. Or one of their dot products is 100 times bigger than the other dot product, even though these vectors have the exact same amount of point in the same directionness. So here's kind of the problem that we get. Dot products do measure same directionness, but that same directionness, that sort of metric of same directionness that you get out of the dot product, is also dependent on the size of the vectors. So they measure same directionness and size of two vectors, which is kind of a bummer. It would be nice if we could find a way to just measure same directionness of two things without having to worry about their size. That would be sort of the ideal. We want things to be just a measure of whether or not they're pointing in the same direction. The good news is we can do that. So in an earlier video, we talked about unit vectors. Unit vectors always have length 1, or magnitude, I should say magnitude. They always have a magnitude of 1. So, but I should say the other thing that we learned about unit vectors is that it's surprisingly easy to turn any vector into a unit vector. All we have to do is find its magnitude and then divide the vector by its own magnitude, and we get a unit vector that has magnitude 1 and points in that same direction as the original vector. So we have a mechanism here that we can use to turn any vector into a unit vector. And if the only thing we ever work with are unit vectors, we don't have to worry about the relative size of vectors screwing up our metric of same directionness, which is nice. So let's do this example here. Let's turn this into unit vectors. Unit u should be, let's see, 3 squared is 9, 7 squared is 49. So this would be 58, square root of 58. So unit u is 3 over root 58 I minus 7 over root 58 j. Unit v would be, let's see, 36 and 440. So this is the square root of 40, which is 2 root 10. Well, if it's 2 root 10, then I can cancel some stuff. I can call this 3 over root 10I plus 1 over root 10j. So these are the unit vector versions of these things, which are the same vectors but shrunk down a little bit so that they have length of exactly 1. And now they have the same length as each other, and the length for the size or the magnitude is not going to influence this dot product metric of whether or not they point in the same direction. So let's find unit u dot unit v. I will get 9 over the square root of 580 minus 7 over the square root of 580, which is 2 over the square root of 580. I don't know what the square root of 580 is, but you could find out if you were ambitious and had a calculator. It's probably about 23, maybe 22. In any case, if you take the dot product of two unit vectors, you get a measure of the same directionness of those two vectors without any consideration of the size, which is what we want out of a dot product. There's more to say about this, but I'm running out of time on this video. The camera is going to automatically truncate things because of the way the memory card is formatted. So we're going to shut this video down. I will be back with part 2 of this video in just a moment.